Okay. So next we will discuss in the next session, next class, maybe in next upcoming classes, we have to discuss grid integration of multi-level inverters. Okay. So for that, there is a prerequisite. So that is this active rectifiers. See, so let us discuss this active rectifiers. So prior to that grid integration, this active rectifiers, these are also known as unity power factor converters. Unity power factor converters, also known as improved power quality, improved uh, improved power quality converters, right, are also known as this active rectifiers. Right. So we have this conventional rectifiers. So those are normally uncontrolled and controlled. So what is the main difference? So between these two, what is the main difference? So between this controlled and uncontrolled. So in case of uncontrolled, so those are mainly with these diodes, whereas in controlled, so those are with thyristors, right? So in case of uncontrolled, you cannot control the output voltage. So but in case of controlled, you can control the output voltage so by changing the firing angle. So let us discuss the drawbacks of these conventional rectifiers. So this is the current waveform. So that is drawn from a three-phase rectifier, so feeding RL load. So you can see that this is the input current waveform, right? So this is the firing angle. I think this is operating at a firing angle of 30 degrees, somewhere around 30 degrees of firing angle. So you can see this A phase, B phase, C phase line currents. Okay, so they are not sinusoidal. Actually, these are non-linear currents. You can see its harmonic spectrum. So this is harmonic spectrum. We have this fifth order harmonic, 7th, 11th, 13th, 17th, 19th, and again this 23rd, 24th. And we have this fundamental, and this is the THD. This THD is around 34 percentage THD. Okay, right. So this is the nonlinear current. So that is flowing inside the AC source. Right. So it is a high THD value, and moreover, so it is producing a sharp rising in the edges. Okay, so this is one drawback, and moreover, on the output side, so how this output will look like, you know this, right? So it look like something like this, right? So this is in case of three-phase rectifier. Okay, so here in output side you have harmonics as 6th order harmonic, 12th order harmonic, and 18th order harmonic on the DC side. But in case of AC side, we have this 5th, 7th, right? So 11th, 13th, and so on. So usually if you have DC side 6th order harmonic, so in that case, we have this 5th and 7th order harmonics on the AC side. So that is general. If you have 2nd order harmonic on the DC side, so in that case, you have fundamental and you have 3rd order harmonic. In case of single phase rectifier output voltage, so it will be something like this, right? So it consists of 2nd order harmonic. So therefore, the source current consists of 2nd order harmonic. So therefore, the source current consists of 3rd order harmonic. Okay, clear? And moreover, right, so it requires a large amount of reactive power. So why reactive power is required? So why reactive power is required? In these control converters or uncontrolled converters, why this reactive power is required? You know that, right? So what is the power factor that actually will operate? If it is a single phase, so what is the power factor? You might have studied different types of power factors in converters, right? So one is the displacement power factor, DPF, okay, and input power factor. So what is the difference between these two, displacement power factor and input power factor? Can anyone tell?
Input power factor is product of displacement power factor and distortion factor.
No, what is the physical thing of this displacement power factor?
Power factor between only fundamental components.
Yeah, that is the power factor between the fundamental current and voltage.
Fundamental
Okay, we
voltage.
assumed that the voltage is sinusoidal, so only the current is nonlinear. So the displacement power factor is the right. So cosine of the angle between source voltage and fundamental source current. So whereas input power factor is, so when you are considering this power factor, right? So we need to consider this entire waveform. Okay, so we need to consider this entire waveform. So when you are considering this displacement power factor, so in this case, so we need to consider the fundamental component inside this load current or the source currents. Okay, so that's the difference. So usually this displacement power factor will be usually greater than this input, less greater than this input power factor. So that is, I think, around this 0.9 cos alpha is the displacement power that is the input power factor for a single phase rectifier, right? So that means when the power factor is always lagging, so therefore it expects some reactive power, right? And moreover, so when it is feeding RC loads, right? So what kind of, we have different loads are there, right? RL load, RC load, and R load, right? So out of this RLE load, so most of the cases we have this RLE loads. So this is especially, so when it is a DC machine, if the rectifier is feeding a DC machine, right? So generally these RL loads are usually not encountered in most cases. So this R load also not encountered. This especially when you are heating application. If the rectifier is used for heating applications, so that is DC heating. So in that case, we have this R load. When it is a motor drive, if you are feeding it a DC motor, so then in that case we have this RLE load. So usually this RL type of load, so we'll never encounter. But you have this RC load. So this is normally, this is common, right? So why RC load is common? So because you have this output, so which is not pure DC, right? If you want to make this pure DC, so what we have to do is we need to connect a capacitor across the output voltage. Okay, so that means now it will become a RC load. So when you have RC load, what will happen? The current waveform is something like this. Okay, so this is the kind of current waveform. So that is normally expected. This is the waveform that is particularly for battery chargers, right? So battery chargers, you normally require a pure DC. To make this pure DC, what normally they do is they will connect a capacitor across this output voltage. So therefore the current will be very high. That means the crust factor will be very high, right? So this is a harmonic spectrum, right? So this is the harmonic spectrum in case of a single phase, so diode bridge rectifier. And these are the recommended values of this IEC. So what is IEC means Electrotechnical Commission. So we have different standards are there for the power quality. So one standard is IEEE 519 1992. So this is one standard. And you have another standard is IEC. So this is IEEE standard, and this is IEC standard for the European Union, right? So these are the power quality standards, so that are used worldwide. So this is according to the IEC recommended values. So what should be the value? So this is for the third order harmonic, right? So this is the recommended value, but it is exceeding this recommended value, right? In all cases it is much exceeding, right? This is the recommended value, so but it is exceeding the actual value. Okay, so whenever right, so whenever some new product or something new is launched, right, so it must be approved by this IEC in European Union especially, right? So in that case, so they will not allow to operate this kind of converters. Okay, so they will not allow for this when you have a harmonic is very high, right? So there are some of the drawbacks with these conventional rectifiers. The first one is they produce a lagging displacement power factor, so with respect to the voltage of utility. So they can generate significant input current harmonics, and they can produce the DC, so with large ripple content, right? So that means the DC is also having large ripple content, right? In AC, input currents is also distorted, but the DC, you cannot produce a pure DC, right? The DC is also not pure, and so it is difficult to regulate the DC output voltage in closed loop applications, right? In case if you are for closed loop applications, we need to use the control rectifier. In case of control rectifier, we need to constantly change the value of alpha. Okay, so whenever we want to change the alpha, so thyristors, once it is triggered, right? So we need to wait until it's commutated. So until the switch is turned off, we need to wait, right? So when first thing is, for example, your switch is turned on at this point, okay? So you know that you need to change the value of alpha. You know that you need to change the value at this point. You know that, so you need to change your firing angle, right? So you cannot directly implement that new firing angle. So you need to wait until the switch is completely commutated. The switch is completely commutated. So after with certain delay, you need to implement this new firing angle. Okay. So that means in case of closed loop applications, when you require some high performance or some high fast response, so in that case, so these are not the good option, right? And limited regenerative capability. So in case of diode bridge rectifiers, so they will not operate in regenerative, right? So regeneration, you know that, right? So if you want to feed the power back to the source, so that is a regeneration. So if you want regeneration, so load must be active. Okay, so generally two types of loads are there: active load and passive load. Active load and passive load. In case of passive load, so they cannot feed back power to the source, but in case of active load, so they can regenerate. That means some amount of power can be fed back to the AC source or any source, right? Okay, so in case the load is active, so some of the energy can be fed back to the source if possible. But in case of these rectifiers, diode bridge rectifiers, so they are not of regenerative, right? Because the diode will not allow the current to be conducting on both directions, or the voltage it can't make negative, right? But this control rectifier can do some extent, right? By changing or by operating the alpha greater than 90 degrees, it can do, or it can work as an inverter. But again, its response will be slow. That means its regenerative capability is limited. Okay, so these are the drawbacks of these conventional rectifiers. So first thing is, it will always demand large amount of reactive power, and it will distort the input current waveforms, and the output that produced is also so not a pure DC. We need to require some filters, and they can regulate the output voltage. That means their closed loop performance is sluggish, and its regenerative capability is also limited. So these are the drawbacks of these conventional rectifiers. Okay. Okay. So these active rectifiers is the solution for this modern rectifiers. Okay. So earlier rectifiers are based on the thyristors or diodes, right? But these are based on the self-commutating devices. So that means these are developed based on IGBTs or MOSFET. So that is self-commutating devices. So this is also known as improved power quality converters or unity power factor converters, also known as PWM rectifiers, or also known as active rectifiers. So all reflect to the same. So they are developed based on the self-commutated devices. So earlier one, that is the conventional one, are based on the forced commutation devices. So now these are the self-commutated devices, right? So we have different classifications of these. We have single phase to three phase, or single phase or three phase. You have unidirectional or bidirectional. So we have this buck type, boost type, or both buck boost type. And we have this non-isolated or isolated. So when you have isolation, so that means there is some high frequency transformer or some transformer inside the rectifier. So these are the different classification of these active rectifiers. Okay, so these are the merits of these active rectifiers. The first one is unity power factor operation. Unity power factor operation. So that means if this is the source voltage, right, the source current is always operated at unity power factor, and it can make, and it is also the source current is always, or we can make the source current sinusoidal. Okay, so that means the THD is practically equal to 0. That means we can, ideally we can make the THD to 0, and unity power factor operation. So they can produce ripple free DC. Okay, so that means we can produce a constant DC and easy to regulate the output voltage. In closed loop applications, you don't need to wait for until the active switch to turn on. So we can directly implement. So that means it's they're fast, and they're having so greater regenerative capability when compared to the conventional converters. So whatever the drawbacks of these conventional rectifiers, so all those drawbacks are addressed here. So one, so that means it doesn't require any reactive power, and it will not distort the source current, and the DC whatever you are getting is a pure DC, and we can regulate the output voltage. So that means for some applications, if you want to increase or decrease the DC output voltage, so we can easily do. And regenerative capability, so that means they are regenerative. Clear? So these are the rectifiers merits. So first we'll discuss the single phase topologies. In single phase, several topologies are there. So the most prominent one are boost rectifier. Okay, boost rectifier. So not converter or boost DC-DC converter, right? So it is a boost rectifier. Another one is voltage doubler circuit. Voltage doubler circuit. Another one is single phase PWM rectifier. Okay, so one is the boost rectifier, voltage doubler rectifier, single phase PWM rectifier. Okay, so first we will discuss the single phase. So later we will discuss the three phase, and later we'll discuss the multi-layer inverter rectifiers. Okay, so this single phase boost rectifier, so this is derived from boost converter. We have this boost DC-DC converter is there, right? So this is derived from the boost DC-DC converter. So if you imagine, if this is the DC voltage, if this is the DC voltage, we have this L, and we have this switch here, and rest of this is the rest of the thing is, so this is rectifier here, and rest of the thing is a boost converter, right? Boost DC-DC converter, right? So that's why it is known as boost rectifier. So let us see so how it will operate. Okay, so this is connected to a single phase bridge rectifier. Single phase, so bridge rectifier. So what kind of output voltage you can expect here? What kind of output voltage you can expect here, right? So this is Vs, so you can expect a mod Vs, right? So that means if this waveform is something like this, so this waveform is something like this, right? That is the rectified output, agree? So this is the output voltage across this bridge rectifier. Okay, clear?
Yes,
So
sir.
now we have this inductor. this a switch. It may be switch, maybe IGBT or MOSFET, and we have this diode and capacitor C. So what is the main difference between the regular DC-DC converter, boost converter or boost converter? So in boost converter, that is DC to DC, right? But whereas here, so you have AC supply here and the output voltage is DC. Okay. So let us assume that, let us divide this circuit into two different modes. So when the switch X, this is the switch X is on. So this is the switch X is on here, right? And this is the switch X is off. Okay. So assume that this is the rectified output voltage. So that means this is in this form. This is the rectified output voltage. So when the switch is closed, the inductor will energize it, right? The inductor will energized and the load is feeding by this capacitor. If you assume that the capacitor is pre-charged or under steady state, so this capacitor is feeding the load, right? This is simple boost converter operation. So when the switch is off, right? So when the switch is off, we have this mod Vs and this is L, right? So both are pumping energy to this capacitor and this load, right? So everything is same as boost DC-DC converter, so except the change that, so here in boost converter we have constant output, so but whereas here, so you will have this rectified output. Clear? So we have two modes of operation. So when the switch is on, the inductor stores some energy. So when the switch is off, right, the source and inductor so simultaneously so pump the energy into the capacitor and feeding the load at higher voltages, right? So that's how this boost converter will work. Okay, it's clear.
Yes, sir.
So am I raising this? Right. So in this circuit, so we need to implement this unity power factor, right? Unity power factor, and we need to regulate this output voltage, right? For example, if you give a reference of 300 volts, the output should be 300 volts only, right? That means the output is regulated to 300 volts. That means the output will follow the reference, whatever the reference you give, right? So it must follow that reference. And the second thing or the other thing is the source current must be sinusoidal, right? So that means this is the source current if you are this is the source voltage if you are assuming that. So in this case, the source current must be something like this, right? This is the source current. The source current must be like this. Okay, the green one is the source current. If you want,
Sir,
this is
screen
the,
is stuck, sir.
now. Is it
Yes, sir,
showing?
whole screen. No, sir.
Just a minute.
Yes, sir. No, sir.
Now it's moving.
Yes, sir. It's no.
Okay.
Thank you, sir.
Right. So if this red one is the source voltage and the green one must be the source current, right? If you want a unity power factor, so this must be the thing, right? So same currents, right? The same thing. Okay, if this is the voltage, right? If this is the voltage, so what must be the inductor current shape? So what must be the inductor current shape? If you want a unity power factor or if you want a sinusoidal, right? So the inductor current must be so in this shape, right? So this is also must be in this shape so that the source current will be sinusoidal. Agree? So that the source current will be sinusoidal, right? If you get an inductor current of this shape, right? So that means automatically the source current will be sinusoidal after before the diode bridge rectifier. So that is the thing, right? So here, so let us assume that, so this is the inductor current. So this is the expected inductor current. So this is in this shape. So then only source current side, right? So you will get a sinusoidal in the source current side. If this is the inductor current, so this will be the source current. So now the question is, so this is the I maximum, right? This is the maximum inductor current or this inductor current, right? So which parameter, so that actually that reflects the inductor current, or which parameter, this maximum current. This maximum current is normally depends on this load, right? So maximum current that depends on the load voltage, and moreover we need to maintain the load voltage constant. So we need to maintain the load voltage constant. Okay, so that means the power, that is the real power that is transferred from this AC to DC. So that means that will reflect the, based on that, so this I maximum can be varied, right? Okay, if you connect a lower resistance, in that case the current will be less. If you connect a means high load, so in that case the I maximum will be higher side. If you connect some small amount of load, so in that case this I maximum will be less. So whatever it may be, so the how much real power actually flowing in the circuit, so that is decided by, or that one decide this I maximum. Okay, so keep that aside. So now come to their actual equations. So let us assume that the switch is on. So this is the equivalent circuit. Okay, so this is the equivalent circuit. So now we are finding out the inductor rate of change in the inductor current. So this is L, right? So this is the rate of change of inductor current. So we can, if we apply KVL inside this one, so we can write like this, right? So L into DIL by dt. So this is equal to this mod Vs. Agree? Agree?
Yes, sir.
In the second
Yes, sir.
circuit, so this is DIL by dt. So this is equal to mod Vs minus V naught. So this is the first circuit and this is the second circuit. Okay, so from the first circuit, this is the first one. So that is the rate of change of current. So this is DIL by dt. And from the second circuit, so this is the rate of change of current. So when the switch is turned off. Okay, right. So now our objective is to control the inductor current, right? So our objective is to control the inductor current. So as somehow we need to draw this much of current from the inductor, or somehow we need to shape the inductor current something like this rectified form, so that the source current will be sinusoidal, right? So that means we need to control the inductor current, right? We need to control the inductor current. So in one of the lecture, when you are discussing the hysteresis controller, so or when you are discussing the current control techniques for the PWM, for the inverters, right? So what is the criteria? So general criteria, if you want to control the current in an inductor, so generally when the switch is on, the inductor current must be increases, right? When the switch is off, the inductor current may be decreases. We have vice versa, right? If the switch is on, we have the inductor current decrease or increase, right? So that means the operation of the inductor current when the switch is on, so it may be increases or decreases, but when the switch is off, it may be decreases or increases. So under that conditions only, we can control the inductor current, right? So that means, so this is switch is on, right? If the inductor current increases, so that means the DIL by dt is positive. When the switch is off, inductor current decreases, so that means di by dt in this case must be negative. If you have positive and negative di by dt's in the inductor current, so then only we are actually control the current, right? So this is the turn on condition, right? When the switch is on, so this is positive or negative? So this is positive or negative?
Positive, sir.
So this is always positive, right? Because the top one is the rectified output. So that means this is always positive. So what about this one?
Negative, sir.
Negative, sir.
So how can you say that it is negative?
That discharging
Positive
is
and
taking place.
No, see here, this is the equation, right? So that is a mod Vs minus V naught by L is the inductor, so rate of change in the inductor current, right? So this is the equation, right? So this is the rate of change of the inductor. So this is positive or negative, so that depends on this V naught, right? Agree?
yes, sir.
Okay,
Yes, sir.
this equation is positive or negative, so that depends on this V naught. So what is V naught? V naught is the output voltage, right? So V naught is the our output voltage. In other words, so what must be the reference voltage? We have this, right? We have this output voltage. We are controlling or we are regulating, right? So that must be the reference voltage. So this is always positive. So if you want to control the inductor current, so this must be negative, right? So this must be negative. So when actually it will be negative? So when this V naught is greater than this mod Vs, so then it will be negative, right? So that means then the output voltage, right? The expected output voltage is greater than the, right? The source peak value, right? This Vs is having some peak, this is Vs is in this shape, right? So it is having some peak value, right? Maybe for example, Vm. So if this V naught is greater than this Vm, so then, so this will be negative. Okay, right? So that means, so what we can conclude that, we can conclude something like this. If this is the output voltage of the rectified output voltage, okay, so it is having some peak value, for example, Vm, right? The reference must be, right? So whatever the reference you are giving, so it must be greater than its peak value. So this is your V naught. So then only you can get a negative di by dt. So then only you can get a negative di by dt. It's clear? So that's why it is known as boost rectifier. So that means it's known as boost rectifier. So if you have AC side, you have some peak value, that is Vm, but the output voltage, so that is always greater than this Vm. Okay? So in one condition you're getting the positive voltage, and the other condition you're getting the negative voltage. It's clear? Okay? Right. So let us design the controller. So for this, right? So you need to shape your inductor current something like this. Okay, so I already said that this is the maximum. So this is the maximum. So whatever the current you are, right, so that is the maximum current. So that means if this source voltage is Vm sine omega t, for example, if the source voltage is something like this form, so Vm sine omega t, that is Vs of t, it is Vm sine omega t. So what is mod Vs of t? So what is mod Vs of t? So it is something like this, right? So Vm into mod omega t. So that is in this shape, right? Agree?
Yes, sir.
Okay. So your current I maximum, right? What is the expected shape of your current inductor current IL naught? So what is the expected shape of your inductor current IL of t? What is the expected shape of this inductor current? Right? So it must be in phase with this Vs of t, right? So it must be in phase with this Vf of t. So that means we can write as I maximum into sine omega t. So that is the inductor current we are actually expecting. Right? So why it is sine omega t? For example, it is having sine omega t plus theta, right? So it is also having sine omega t plus theta here. So here also it is having sine omega t plus theta form, so that these two Vs of t and so this IL of t, so both are in phase, so that the source voltage Is of t, that is the source voltage, so that is in phase with Vs of t. Clear? Right. So how this Vs of sine omega t plus theta can be obtained? Right. So this is obtained by using the source voltage. So this is obtained by the source voltage. Right. So let us come to this controller. So we have this V reference. Okay. So we have this V reference, and this is the reference. This is the reference value, and this is the actual voltage across the load. Right. So this is the actual voltage across the load. Okay. So we are given to a PI controller. So we are given to a PI controller. Right. So that means these are operating in closed loop, right? So therefore we need to give to a PI controller. So what is the purpose of this PI controller? So that will make the steady state error 0. That means it will track this V0 to follow this V reference. Right. That means the difference between the V reference and V0, practically it is making to 0. Right. So we already discussed that. First, that means whatever we are maintaining the capacitor voltage constant depending on the real power transfer, right? So based on that, we can expect that, right, the output of this PI may control the I maximum, right? Clear? So the output of PI may control this I maximum. Is clear? So now we got this I maximum, right? You got the I maximum. Next we need to generate the reference current for the inductor. You will generate the reference current for the inductor, right? That reference current is I maximum sine omega t plus theta shape, right? So that means how to get the sine omega t plus theta. So this is the source voltage divided by, if it's dividing peak value, so what you will get here, only sine omega t plus theta you will get, right? You will get mod sine omega t plus theta, so with this expression. So this is the entire thing. Now it is I maximum, right, sine omega t plus theta. I maximum sine omega t plus theta. So that is the expected current through the inductor. Okay. So now by using this hysteresis controller or sine PWM or triangle carrier controller, we discussed two methods, right? So one is the hysteresis current controller based, and another one is the triangle carrier current controller, right? So by using any of this technique, right? So we'll try to follow this reference. We'll try to follow this reference. Okay. So we already discussed, right? If it is a hysteresis controller, some hysteresis band is defined, right? So when the current is less, the switching is done something like this, so that the output voltage can be, the output current can be controlled. So that is ultimately giving to the firing signal for the switch. Clear? It's clear?
Yes.
It's clear. So you have any
Sir?
doubts on this? Yeah.
Sir, can you please explain that PA controller part one more time?
PI controller. So here there are two objectives we have, right? We have two objectives here. The first objective is to maintain the output voltage or load voltage constant, right? To maintain the load voltage constant. And the second objective is to make the source current sinusoidal, right? So there are two objectives. So that means outer we have voltage control. So this is outer voltage control, and we have inner current control. So this is voltage control, and here inside this you have current control. Okay. So we are making the load voltage constant, and at the same time we are maintaining the current sinusoidal. Okay. So here, to maintain a constant voltage across load or a constant reference, right? So as already we discussed, this reference must be greater than the peak of source voltage. This reference, when you're giving this reference, right? So this must be greater than the peak of source voltage. So then only it will work, right? So that means it is always operate in boost mode only. So this is in actual voltage. So by using some sensors, we will measure the load current, load voltage, and we will compare with the reference load voltage, right? By using PI controller. So what is the object of this PI controller? So it will make the steady state difference between these two 0. Okay. So we can expect that the output of PI controller may be this I maximum. Okay. So that means, right. So it is I maximum. That means it will control the overall magnitude of the current. So obviously it will control the overall magnitude of the current, right? So now the next step is we need to generate the reference current for the inductor. So inductor reference current we assumed as I maximum sin omega t plus in this form. So I maximum you already obtained. So that next thing is we need to multiply with this mod sin omega t, right? So this is mod sin omega t plus theta. So there is a mistake here. So it is divided by Vm. Okay, so Vm is the peak of the supply voltage. So we are multiplying with this one. So that means that generate the reference signal for the inductor current. And this reference signal we are controlling here, or this reference signal, whatever that reference signal is trying to, this actual inductor current is trying to track the reference signal, right? So that this reference signal may be in this shape. Okay, right. Clear? So that this is the reference current. So obviously the source side current will be sinusoidal. Is clear?
Yes, sir. Thank
Okay.
you, sir.
So this is about the controller. So we have some results are here. We have some results are here. So this is reference they set as 400, right? Reference they set as 400 in this particular example. You can see that this is the reference they set as 400, right? So at the same time, you can also see that the right. So you can see that this is source current, right? The source current are in phase with the source voltage. This top one is the source voltage, right? This is the source voltage, and we have the source current. So both are in phase. So both are in phase. So at this particular time, one second. Right. So at particular time, so we are trying to increase the current. The current is increased here, right? So we are trying to increase the current. Okay. So whenever we are trying to increase the current, so what will happen? So there is a slight reduction in the output voltage, right? If you are increasing the current, so normally what this is known as a speed control, right? So whenever some it is rotating at some speed, right? Okay, something is rotating at some speed. If you suddenly increase the load, what will happen? The speed will reduce, right? The same philosophy here, it is having some charge. So whatever, right, when you are increasing the load, so it demands more current, right? Or it is demanding more power, or it is demanding more energy. So that excess energy, that energy is instantaneously fed by this capacitor. So therefore its voltage is slightly reduced. But actually the control is working here. So that means after some time, the control is maintain the steady state, or the control is increased the voltage, right? So now as and when the load is reduced, so as and when the load is reduced, what will happen? Again, for example, if you remove the load, the speed normally generally increases, right? The same thing here, the capacitor voltage slightly increases. After some time, again, it reached the steady state value. So you can see here, right? So this is how it will vary. So that means irrespective of the load conditions, so more or less the output voltage is maintained constant, and moreover, right, and moreover the source current is also sinusoidal. The source current is also sinusoidal in this case. Clear? This clear? It's clear?
Yes, sir.
Yes, sir.
So here in single phase boost rectifier, so there is one, this is not regenerative. Okay, this is the circuit. Right. So this is not regenerative kind of thing. So why it is not regenerative? So why this topology will not fed back to the source?
Unidirectional diodes.
So because we have this diode is there, right? So this will not allow the current in both direction, and moreover we have this bridge rectifier. So this is of non-regenerative type. Okay. So this is always non-regenerative type. And another thing is that, right, so whenever generally this output voltage is something like this, right? Okay, the output voltage primarily something like this. So in the output voltage, so there exists a second order harmonic. Okay, second order harmonic, for example, if you have 50 H supply, in output voltage usually we have this 100 H supply, right? So some 100 H component will be present in the output voltage. So this 100 H component, so usually it will distort the source voltage. So we already discussed that when you have the second order harmonic on the source side, we have this fundamental and the third order harmonic on the AC side. Okay. So that means the second order harmonic in the output voltage, so especially the output voltage that produced in this diode bridge rectifier, so that will produce a third order harmonic in the output side or the input source current side. So therefore, the best practice is we need to eliminate this. We need to eliminate this second order harmonic in the circuit. So what usually do is, so this is the actual voltage we are measuring, right? So this is the voltage we are measuring. So before that, so we normally connect a filter. So this is the 100 H filter. So notch filter. So that means that will remove the 100 H component. So this is the V0 actual. So by doing so, right, this inductor current is free from the third order harmonic. Yeah. So usually we connect a low pass filter or some high pass filter or some other kind of filter, or you can use some low pass filter you can prefer. And another thing is, in this case we use this hysteresis controller. So we can also use this triangle carrier controller. If this is the IL reference, right? And we have this, so IL actual, and this is again controlled some one PI controller, so that will decide the modulation index. We have these signals, and it is compared with some triangle carrier. So this will generate the firing signal for the X. Okay, so this is hysteresis control based. Either you can use hysteresis controller or you can use some triangle carrier controller. So the ultimate aim is to control the output voltage, DC side voltage, and make the source current sinusoidal and in phase with the source current. Clear? Okay. So next topology, we'll come back to this. So next one is PWM bridge rectifier. PWM bridge rectifier. Right. So this is what it look like. It look like a simple H bridge inverter, right? It look like a simple H bridge inverter, but actually it is doing AC to DC. Okay, it is actually performing AC to DC operation. So normally we have, it is fed from a DC source, and this AC terminals are usually feeding to some load, right? Some AC kind of load, right? But its operation is different. So it is we are operating as a AC to DC rectifier. Okay, right? Clear? So here this T1, T4 are operated together. So T1, T4 are operated together with this T3 and T2. So T1, T4 are operated together with these opposite switches T2 and T3. So again, all these PWM rectifier, so this inductor is must. Okay. So why it is must? So whenever you are trying to control the current, so then the inductor is always necessary, right? So if you are trying to control the current or some current control operation, so we can only perform so when you have inductor in the circuit. So this is Vs, source voltage. So let us assume that the switches T1, T4 are turned on. So let us assume that the switches T1, T4 are actually turned on. So this is the equivalent circuit. So when this switch is on, so this switch is on, so it will be like this. So this is the equivalent circuit, right? So that means this capacitor charges like this. For the same case, right? So for the same case, if opposite switches T2, T3 are turned on, so how it will be? If the opposite switches T3, T4 are turned on, so how it will be? It will start like this. Okay? It will be, yeah, it will be end in this direction, right? So that means the capacitor will be charged in the opposite direction. So for this particular case, so obviously for T1, T4, if you turn on, you will get positive voltage. So when you turn on T2, T3, so you will get the negative voltage, right? The same thing is reflected here. Okay. So let us write these equations. So let us try to write these equations, right? This is the inductor voltage. So that is L into di by ds. So if you apply KVL here, so in this case, so this is source voltage Vs of t, and this is minus V naught. So in first case, so to Vs of t minus V naught, and the second case, so this is minus plus here, right? So this is also minus plus. So therefore it is Vs of t plus V naught. Clear? So we have two cases, Vs of t minus V naught and Vs of t plus V naught. Clear? It's clear? So here, according to our current control principle, so one current must be positive, one di by dt must be positive, and the other must be negative, right? So and the other must be negative. Clear? So now, so which one we can make negative and which one we can make positive? Normally this one will make, we can make this negative, right? So when this will be negative and when this will be positive, so what is the common constraint? So when this is always negative, so when this is always positive.
V naught is greater than Vm.
V naught.
If this V naught, right, if it is greater than, right, this Vs of t peak value, right, in other words, if V naught is greater than this Vm, so under this case, so this is always negative and this is always positive, right? So this is, imagine, so this is the voltage. If this is something like this, right? So this is Vs of t and this is V naught, right? If we add these two together, right? If we add this one and this one, this is one and this one and two, if we add, right? So this is always positive, right? Similarly, if you subtract this 2 minus 1, so that is always negative. So here also the output voltage must be greater than Vm. The output voltage must be greater than Vm, or peak value of supply voltage. So then only you can get the source current sinusoidal, or we can control the current and we can make the output voltage constant. Okay. So in this particular case, right, so this is the source voltage, it is in this shape. So we want to make this source current sinusoidal, right? So here inductor is connected here. So what is the current of what is the expected waveform to this inductor, or expected current that is flowing waveform of the current waveform through the inductor? So earlier case, so inductor is connected after the diode bridge rectifier, right? So now it is connected in series with the source. So that means here if you want unity power factor, the inductor current must be in phase with the source current. That means the inductor current must be in this form. You understand the difference between these two? So in this particular case, it is connected after the diode bridge rectifier, right? So this is connected after the diode bridge rectifier. So that means you can get a rectified output in the inductor current, so that this will be sinusoidal. So whereas here, whereas here this inductor current must be in phase with the source current. So then only source current and inductor current both are same, right? So here source current and inductor current both are same. So in earlier case, so both are different. So that is the main thing. So we need to write. So that means the inductor current, we have this I maximum into this sine omega t. So not mod sine omega t, right? So remember, not mod sine omega t. So this sine omega t must be obtained from the source voltage, right? We have some source voltage Vm sine omega t form, right? So we need to divide with peak value Vm. It's peak value Vm. So from that you can get the sine omega t. So usually the sine omega t, right? So that means we have Vm sine omega t, and we are dividing with this Vm, right? So this sine omega t, we have only the sine omega t, right? So this is normally known as unit template. So this is known as unit template. So that means its magnitude is varying from +1 to -1 or +1 to 0 or 0 to -1. Right? So it is known as unit template. Clear? Right. So we have this controller. Right. The controller is same as previous one. So we have this reference voltage here. So we have this reference voltage, and this is the actual voltage. Reference voltage minus actual voltage, and we have this voltage PI controller. So that will gives you the I maximum. Right. So this I maximum we need to multiply with the sine omega t. So it is we need to change here. So this is Vs by Vm. So this is actually Vs of t by Vm. Okay. So that means it generated the I maximum. So that means this is I maximum here. So this is the source current now we need to measure, right? Or source current, inductor current, both are same. So this is the reference source current or the reference inductor current. So this is the actual inductor current or the actual source current, both are same. And we have this current controller, right? So when it is greater than that, we need to turn on this T1, T2. When it is less than that, we need to turn on this T2, T3. That means we need to turn on T1, T4. I think this is wrong here. So this is T1, T4, and this is T2, T3. Okay. So according to the switches, we need to turn on T1, T4 and T2, T3 alternatively. Okay. Clear? It's clear? So this is how this single phase PWM rectifier will work. So interesting thing is, so it is of regenerative type, right? So this one is of regenerative type. So earlier, whatever we discussed, that is boost rectifier. So that is non-regenerative because the diode will prevent the current to flow in the other direction. So whereas this one is regenerative. So he can see that the regenerative operation. So if it, this is this, if it is waveform, I will erase this. Okay. So it is normal operation. If this is the sine wave, so in case of normal operation, it will be like this. Okay. So that means the power, if you multiply this power and this current, voltage and current, right? You can see that the power, so how it is varying, right? So the power will be something like this, right? If it is something like this, so both sides it is positive. So whereas here, okay, you can also you can see that the unity power factor is maintained. So but whereas here you can see it's regenerative. So whenever there is this is the source voltage, if you assume that the current is in the opposite direction, the current is opposite direction. So that means the instantaneous, if you multiply this voltage and current, so this gives you negative, this gives you negative, and this also gives, so everything gives you negative, right? So that means the power is actually feeding back to the source, and at the same time it is maintaining the unity power factor. So unity power factor operation and feeding back to the source. That means regeneration with unity power factor. It's clear? So that is the main thing. So with the PWM bridge rectifier, so it is regenerative type. So now the point is how to make it regenerative. So when actually it will regenerate. So when actually it will regenerate. So if you want a regenerative, so it must be, the load must be active load, right? This load must be an active load. So that means, for example, if you connect a DC machine here or some DC machine here, the DC machine so must operate as a DC generator. So then only the power is fed back to the source, right? So here, some example, that means we need to connect a, for example, if you want that, so it must be act as a DC generator. Or you need to connect a large battery and make sure that, so for example, this is 200 volts, we are maintaining 200 volts across this one. So it must be the generator voltage, so must be greater than this 200 volts. So then only the regenerative can occur, right? If it is around 230 volts or something like this, right? So then only this regenerative can occur. Clear? So load must be active and it must be greater than the output voltage. So whatever this difference, these both are connected in parallel, right? So this is 200 volts. For example, if you consider this 230 volts, right? This different 30 volts. So this 230, right? Clear? This difference 30 volts, whatever is there, right? So that is consumed in this resistive load. So that means this is 230 volts. So assume that this is 200 volts, right? So we are connected a battery or some DC motor, that is 230 volts. So we have some external resistance, we have some regenerative resistance we need to connect, right? So that means the voltage across this one is minus 30 volts, that is drop. So overall, so both voltages are same. That means this voltage and this voltage is again 200. So therefore we can assume that both are in parallel. Clear? So this is about this boost single phase PWM rectifier. So we have this other topology, so that is voltage doubler circuit. We have this voltage doubler circuit. The circuit topology is simple. It is like this. Okay, it is same as the PWM rectifier. In case of PWM rectifier, we used the full bridge, right? Full H bridge. So here we used only the half H bridge. Right, this is one phase leg. So the remaining phase leg is composed by two capacitors, and the midpoint of these capacitors are connected like this. Okay, the midpoint of these two capacitors are connected like this to connect it to the AC source. Same things, right? So earlier one is a full bridge inverter. So this is the off bridge inverter. So nothing changed, right? So this is, we have only two switches, right? This is the equivalent circuit. So when switch T1 is on, and this is the equivalent circuit. So when switch T2 is on. Okay. So in both cases, in T1 is on, so that means this capacitor charges like this. Right. So when T2 is on, the capacitor charges in the opposite direction. And these are the corresponding equations. So Vs of T, Vc1, and assume that this is the first capacitor voltage is Vc1, and the second capacitor voltage is Vc2. So now what will be the condition? Right, if you want to make this one as negative, right, if you want to make this one as positive, so what will be the condition? So in this case, what will be the condition? So this Vc1 so must be greater than Vm. Similarly, this Vc2 must be greater than Vm. Okay. So this Vc1 is also greater than this Vm. So Vc2 is also greater than Vm. But so load is connected between, right? So whereas this load is actually connected between, these two are in series, right? So load is connected in the series connection. So that means whatever the voltage, this Vc1, if you assume this both are same, so you will get 2 Vc voltage here, right? That means you will get Vc1 plus Vc2 voltage. So Vc1 is greater than Vm, right? And VC2 is also greater than VM. So therefore, effectively this voltage will be doubled, right? So that's why it is known as voltage doubler circuit. Okay, right. So in this case, the simple example, so if this is the source voltage, right? If you keep this VC1 here, say for example this is 200 volts, so say we can keep this 300 volts here, right? The combined output we have similarly, we have this VC2 also, right? So VC2 also is maintained 200 volts, 300 volts. So that means the overall output voltage is around 600 volts. Okay, so due to this reason, so this is the output voltage is doubled. So that's why it is known as voltage doubler PWM circuit. Is clear? So we need to make sure that so each capacitor voltage must be greater than the peak of supply voltage. Clear? So there is some drawback with this exact thing, right? So when you are discussing the three level diode clamper, right? So in that case, the capacitor is actually flowing inside this capacitor, right? So here this current is actually flowing inside this, right? So either this upper capacitor or this bottom capacitor, the voltage will be some disturbance will occur, right? So between these two capacitors, when actually a current flowing, right? This is the two capacitors are connected like this. If actually current is flowing inside and away from the circuit, then this capacitor voltage will be affected. So we already discussed in case of this neutral point clamped at this diode clamped inverter, right? The same thing. So here also, so there will be some disturbance in this capacitor voltage. So that disturbance we can address by just modifying the controller. So this is the one. So this is the input voltage. So this is the reference voltage, and this is the output voltage. Right. So this is the reference voltage, and this is the output voltage. Right. We have to make sure that so this V0 reference, right? So usually greater than, that means we need greater than VC1 and VC2. So both must be greater than VM. Okay. If VM is 200, if you want to operate it for 300, so that means this V reference must be 600. So 2 times the capacitor voltage, right? So this is the actual voltage, and we have this PI controller, and again you'll get I maximum. So that is, we are multiplying with unit template, right? You are multiplying with unit template here. So from this you get the reference current. Okay. So here something we need to add some extra thing, right? Some extra thing is there. So what is that extra thing is? So we need to tightly control this capacitor voltage. So what we can do is, so whatever the difference between these two capacitors, so that we can equate to 0, right? The sum of these two capacitors, we are equating to the reference value, and the difference we are equating to 0, right? So that means the sum, for example, this VC1 and so VC2 are there, right? The sum of these two, for example, it is controlling 600 volts, and the difference we are controlling, we are trying to control to 0. So that means under steady state, we can expect that at some point this one voltage is 300 and another voltage is 300. So then only this condition can be achieved, right? In both ways we are controlling, the sum will be equal to the actual reference, and the difference is also we are controlling by using some PI controller. So whatever that offset is there, right? So the offset is we are adjusting here. Okay, the offset we are adjusting in this reference signal, right? That offset we are adjusting in the reference signal, and rest of the thing is we have this hysteresis controller or the sine triangle PWM controller. So this is the offset we are getting, and this is the reference signal actually we are getting, right? It's clear? So this is the output voltage, this is the source voltage and source current. We can see that some switching is, because this is due to the some switching. So we can expect that, so this waveform is almost unity power factor, and it is also sinusoidal. So you have any doubts on this? Okay, if you have no doubts, we will move to its applications. So where exactly these converters are actually used. Yes. Yeah. So this is one example. This is the train locomotive, that is a train engine, right? So it is a train engine, especially in train engine. So they're using nowadays. So engine may be of we have different engines are there, right? So in case we have some DC motors are there, and now DC motors now they are replaced with induction machines also, right? So we have this transformer, that is the line transformer here. Okay, so by using this PWM rectifier, this is PWM rectifier. So we are converting to this DC. Again, this DC is feeding back to the either AC, or if the motor is of a DC, so directly it is giving to the supply. So this remaining part, so that all depends on the motor inside this locomotive. If it is a DC motor, so directly this PWM rectifier is sufficient. If it is a AC motor, again the DC is converted back to AC. So the main advantage here, so this is 4 quadrant, right? So that means the power we can feed back to the source side. Power actually we need to feed back to the source side. So this is some schematic of this locomotive, that is a train engine. So this is also used in electric vehicle chargers. So we have this charging circuit. Okay, so we have this battery charging circuit. So 2 different types of chargers here. Okay, so first one, you can see, you can start from here. So this is AC source. Okay, so this line is there, right? This is on board. So that means inside vehicle. And this is off board, means that is outside vehicle. Okay, we have inside vehicle and outside vehicle. So we have this outer side, so that means this is normally operate with 110 volts or 220 volts. So depending on, usually these batteries are operated with 110 volts or 220 volts, right? If you can see that your battery chargers or your phone charger, so you can see 110 volts or 220 volts, that is written on that, right? So we have this EMI filter, just to filter out. So after that we have this rectifier circuit. Okay, and we have this boost. This is what kind of circuit it is? Boost rectifier, right? So this is the boost rectifier. Okay, this is the boost rectifier. You got a high frequency, so AC voltage you got here. So DC voltage you obtained here. So this DC voltage we converted to a high frequency AC supply by using this inverter. A high frequency AC circuit or high frequency AC is converted, and we have this high frequency transformer. So HFTR means high frequency transformer. So we need to always provide the isolation between this charger and your mobile phone or your vehicle or anything, right? So this high frequency oscillation, this isolation is provided by this high frequency transformer. So inside the vehicle or inside your mobile, so we have another coil, right? So that is another winding of this high frequency transformer, and that is converted actually to the DC. So that is actually converted to DC. Clear? So here we normally use this unidirectional switches. So because we cannot expect that the car will charge the other thing, right? Your mobile will not charge the source, right? So that's why we have this unidirectional switches. Okay, so this is one configuration by using this boost rectifier. That's first one we discussed. This is the same thing, right? This is the same thing with PWM rectifier. So this PWM rectifier, it will generally simplify the circuit, whatever we have this, right? The circuit will be simplified. So this is off board, so outside the vehicle, and this is the inside vehicle. So we have this AC supply is there, right? So AC supply is converted to a high frequency AC here. This we have this bidirectional AC to DC converter. So AC is converted to DC here, and DC is converted to high frequency AC. and again we have this other circuit on the battery side. Okay, so this is isolated bidirectional this chargers. So this topology is especially known as, this is known as dual active, so bridge rectifier. Maybe we'll discuss in later classes. So this is another one, so another application, so which is used inside the UPS, so which is used inside the UPS. Okay, this is, you have input supply here and some filtering here. So this is converted to, this is PWM rectifier. Okay, and this is the battery, right? So either these batteries are there, or if it is, we have two different types of UPS, right? Online UPS and offline UPS. And so this is DC to AC conversion, right? So this is DC to AC conversion, and it is feeding to this load. So we have this rectifier and inverter, and their jobs will be interchanged. If this AC source is not there, right? If this AC source is not there, so in that case it is fed from the battery only. So another one, that is the low cost motor application. So this is a 3-phase with single phase supply. We can actually obtain a 3-phase supply, right? So whatever this inside this one, so this is, you have AC to DC conversion and DC to AC conversion. This is used in low cost induction motor. So this entire thing, right? So this one is AC to DC conversion, and this is DC to AC conversion. So this midpoint, right? So it is using, in this case, it is using, you have A phase, B phase, C phase, right? So this midpoint, we are using it as a C phase. So this midpoint, we are using it as a C phase. Okay. So this is the UPS with voltage doubler rectifier circuit. So this is another application. So UPS we are using as a voltage doubler circuit. Okay. So these are the applications we have. So far we discussed a single phase. Maybe in the next class we will discuss 3-phase. So you have any doubts on this? So you have any doubts? If you have any doubts, you can ask me. Otherwise, we will stop here. Yes?